Hello, my name is Masoor from Physics 2211, Section NO2, Georgia Tech, and today I did my lab on spring mass force. The objective of this lab is to analyze the oscillating motion of a mass on a spring using Newton's second law and the energy principle. In this lab, the motion of the block during the experiment very closely follows the motion of the block during the computational model. This is the video I analyzed using Tracker. I was able to calculate the location of the block of mass through each frame. Using these points, these graphs were calculated. The given data in this experiment are: the initial velocity is 0, the mass of the block attached to the spring is 0.402 kilograms, the total time is 7.692 seconds, the length of the spring is 0.7 meters. We want to use the energy principle, which is total energy equals kinetic energy plus the potential energy of gravity plus the potential energy of the spring equals 0. Hooke's law, which is force equals stiffness times displacement, and Newton's second law. Using this graph that I obtained from my tracker points, I'm able to calculate the period of oscillation. And to calculate the period of oscillation, what you do is you take the total time that it takes for this graph to hit 3 valleys and then divide it by 3. So, given that the period of oscillation is 1.47 seconds, we are able to find the stiffness of the spring by inputting the period of oscillation into the equation 4 pi squared times mass divided by period of oscillation squared equals stiffness. We then get stiffness equals 7.336 newtons per meter. After finding the stiffness, we are able to calculate the relaxed length of the spring by plugging it into this equation. L0 equals magnitude of L minus mass times gravity divided by stiffness. We then get L0 equals 0.163 meters. These are the formulas I had to implement into my Python code in order to get a correct computational model of the spring force. When I run my computational model, this is what I get. On the screen on the left, you see this blue ball, which represents the position of the mass as my computational model will interpret it, and the red ball represents the actual position of the mass calculated using Tracker. As you can see, they almost exactly match up. So much so that you can't even see the red ball behind the blue ball at the end of the 7 seconds. This black arrow going down represents the force of gravity, and the blue arrow going in the direction of the spring represents the spring force. This graph on the right, what you see is a graph of the energies. The blue line represents the kinetic energy, the green line represents the potential energy of gravity, the red line represents the potential energy of the spring, and the yellow line just represents the green line and the red line added up, which is 0. The next question asks us to estimate the period of oscillations across the x-axis and across the y-axis. Well, for our code, we had already deduced that the period of oscillation for the y-axis was 1.47 seconds. Using the same method, we calculate the period of oscillation to be 1.62 seconds for the x-axis. This is because the weight moves further along the x-axis than it does in the y-axis, almost in an elliptical-like motion, with the longer axis being the x-axis. You can see it in the video as shown. As you can see, the spring is moving the massive block more left and right than up and down.